All right, and let's begin. Hello, everybody. My name is Matthew Banzer. Welcome to Headworks' Biological Nutrient Removal webinar, and we're going to be joined today by Somnath Basu and Siva Angappan.
Okay, thank you. And I'm going to start. I'm
Awesome.
Somnath Basu, and I am with Headworks International. With me is Mr. Siva Angappan, also of Headworks International, and he is our technical director and located in the Victoria, British Columbia office of Headworks. And I'm located in the headquarters of Headworks International, which is in Houston, Texas. Thank you. And I'm starting right now. Here in this slide, we have given an idea about what are nutrients. What is the definition of nutrients? So nutrients are the elements that are necessary for the microbiological cells to maintain their growth. And you can see the table on the right-hand side of the slide, which shows the chemical constituents of a bacterial cell. And typically, you can see that there are nutrients which are nitrogen, phosphorus, and potassium. And there are also micronutrients: calcium, magnesium, sulfur, boron, copper, iron, manganese, molybdenum, zinc, and chlorine. So these are the elements that make up the microbiological cells. And because the majority of the constituents are nitrogen, phosphorus, and potassium, they are very important and they are termed macronutrients. Okay, so now nutrients are required for any living cell. It's not just the microorganisms or bacteria. For any living being, nutrients are necessary for the growth of the cells. So even our human body cells, the plant cells, they all need nutrients. And for example, you can see plants contain about 80 to 90% of water. The rest of the mass, the dry parts of the cell, are consisting of cellulose, hemicellulose, pectin, lignin, and mineral matters. And the elements that make up the cells are carbon, oxygen, hydrogen, which is 95%. Then macronutrients, nitrogen, phosphorus, and potassium. And then micronutrients, total of about 5% of the constituents, which is 100% of the cells. And while nutrients are essential for the growth of the microorganisms that participate or that mediate the wastewater treatment reactions. At the same time, they also mediate the growth of aquatic vegetation, which are in most cases quite undesirable. And a discharge of these nutrients in uncontrolled manner to the receiving water bodies can lead to the growth of such aquatic plants, which create nuisance odors, the poor health of the water body, and they make the water unsuitable for beneficial use. The aquatic vegetation, which we were talking about, they are photoautotropic, which means that for their growth, they extract energy from light. And the carbon that is needed for the cells to grow, that they derive from the atmosphere, inorganic carbon. The chlorophylls in the plant body, they absorb the sunlight and they mediate the photosynthetic reaction. So what is the photosynthetic reaction? It's given in the form of the chemical equation, that is carbon dioxide from the atmosphere, water from the aquatic environment, and light energy, which is expressed as h nu or photon, that make the glucose molecules. And glucose is the organic molecule that they feed on to grow. So glucose, as they polymerize, it becomes cellulose, hemicellulose, lignin, etc. And that forms the building blocks of plant cells. So this gives a very overall idea about how the plant cells are formed. And why we are talking about the plant cells here? Because these are the plants that grow in the aquatic environment and that assimilate the nitrogen, phosphorus, and other nutrients that are discharged from wastewater treatment plant, and then they use those nutrients to grow. And when the growth is uncontrolled, then they create or they render the water body unsuitable for use. And this is something that is called eutrophication. And we'll see that definition in the next slide. So in the plant body, about 1 to 3% by weight is nitrogen, and 0.1 to 0.6% by weight of the dry cells is phosphorus. So nitrogen and phosphorus, they play a big role in the growth of aquatic plants. And natural ecosystem can't provide this, so they need to be supplemented externally. And what is the external source? That is the wastewater discharge from the treatment plants that contain nitrogen and phosphorus, which are the nutrients. Okay, and this gives an example of a few of the aquatic plants and their nitrogen content. And you can see the variation of nitrogen content. This comes from the research, and the studies found the nitrogen concentrations in the different types of aquatic plants. And you can see the phosphorus concentration. Obviously, there is a large variation, but you can see the statistical distribution, which gives the minimum and maximum range. And also the R factor is R is the ratio, and the M, which is the deviation, standard deviation, and N is the data points. So this gives you an idea about the phosphorus and nitrogen content of the aquatic plant cells. Okay, so as I was mentioning, basically, what are the sources of nitrogen and phosphorus in water bodies? So there are two major sources. One is the discharge of domestic wastewater, which originate from human and food wastes. And there are many complex organic compounds that are present in both dissolved and colloidal forms, which make up the organic part of the wastewater, which is expressed as the biochemical oxygen demand. And then there are nitrogenous compounds that are present in ammonia, protein, RNA, DNA, etc., which are present in food waste and also human waste. So bulk concentration of ammonia and organic nitrogenous compounds are expressed as total kilojoule nitrogen, or TKN. Domestic wastewater that comes into municipal sewage system consists of primarily carbon, oxygen, nitrogen, and phosphorus. And of course, there are other minor elements or micronutrients. An empirical chemical formula of domestic wastewater is C10H19O3N. And when this wastewater, this is raw wastewater, when this wastewater is treated in a treatment plant, then majority of the organic compounds are oxidized. BOD is removed to more than 90%, and then also TKN, or nitrogenous compounds, are consumed by the growth of the microorganisms that carry out the wastewater treatment. And then there is also another type of source, which is agricultural runoff that comes from the chemical fertilizers. Examples are urea, NPK, and MAP, DAP, phosphate fertilizer. So this MAP and DAP and NPK, as you can see, they contain both nitrogen and phosphorus. NPK contains also potassium, and these are applied for agriculture for plant growth, to aid in plant growth. Urea contains nitrogen. Okay, so as I mentioned earlier, excessive release of nutrients lead to uncontrolled growth, and these discharges are point sources, and high nutrient concentrations promote the growth of aquatic plants which are undesirable. This is called eutrophication, which renders the quality of the water poor, and also it becomes aesthetically and also from beneficial use point of view, they are poor. They cannot be used for any beneficial purposes, for recreation, for drinking, for industrial uses. If there are large growth of undesirable aquatic plants, then they are not useful. So EPA has come up with the guidelines for the discharge, the concentration of the discharge, and these are contained in the Federal Clean Water Act, and these are maintained by the NPDES permit. These are governed by the NPDES permit applications, National Pollutant Discharge Elimination System, for the discharge of pollutants through point sources like wastewater treatment plant sources. A generic requirement for this NPDES permit is BOD and total suspended solids less than 30 milligrams per liter each. But above and beyond that, the local regulatory bodies also impose certain other conditions, and most typically these are nitrogen, ammonia, total nitrogen, and phosphorus. So we'll look at that. I was talking about eutrophication, and this slide shows you an example of the effects of eutrophication. What happens to a pristine water bodies when there is uncontrolled discharge of nutrients and when there is uncontrolled growth of aquatic plants, as you can see in this slide. When there is a discharge from wastewater treatment plant, if the treatment plant is designed and operated for BOD removal only, then there is no removal of ammonia. Just ammonia itself is harmful for the aquatic life, for the organisms, fish and other types of aquatic life, because ammonia create aquatic toxicity and it also removes the dissolved oxygen. So there is a shortage of dissolved oxygen that the aquatic life, fish and other types of aquatic life depend on for their own sustenance. So that's why at many locations, regulators ask for removal of nitrogen, and that removal is done by nitrification, and the product is nitrate. Ammonia is converted first to nitrite and then to nitrate. But nitrification of ammonia does not remove nitrogen, which is a part of nitrate. As you can see, nitrogen atoms are part of nitrate. It removes the toxicity, it removes ammonia and the ill effects of ammonia, but it does not remove nitrogen, which contributes to nitrification. So like ammonia, nitrate also contributes to eutrophication and adversely impacts water bodies. So how do we do that? Like BOD removal, ammonia and nitrogen removal also are conducted by wastewater treatment plants when they are designed and operated accordingly. Now, going back to the fundamentals of wastewater treatment processes, you can see from this slide, there are two basic types or basic classes of wastewater treatment processes: the suspended growth or activated sludge process and attached growth. Activated sludge process consists of microorganisms which are suspended in the aquatic system in the wastewater, and it can be batch, it can be continuous. The batch are sequencing batch reactors where it is in sequence. It operates in batch, but in sequence. Continuous, as the term says, it is conducted in reactors with continuous flow of wastewater. And in that wastewater tank, treatment tank or reactor, there is a population of microorganisms that conduct the reactions to remove BOD by oxidation and ammonia also by oxidation to nitrate. Attached growth processes, as opposed to suspended growth, they grow. The microorganisms are attached as films on surfaces of media, and these media are made up of synthetic materials like polypropylene, polyurethane, or even rocks. So depending upon the type of reactor, these are the different types of media. There are different types of media that are used in the industry. And then there are dynamic film, fixed film media, static fixed film media. Static fixed film media are trickling filters, then biologically active filters. And we have explanation for those in the next few slides. And dynamic fixed film is rotating biological contractors and moving bed reactors. And in between, the hybrid treatment system that takes advantage of the benefits of both activated sludge process and fixed film processes. So it's a hybrid process and it's called integrated fixed film activated sludge process, or IFAS. This slide shows the chemical reactions. The BOD oxidation that I just mentioned is the basic chemical reaction is BOD. BOD represents organic compounds that are present in wastewater, and that is oxidized by oxygen, and oxygen is supplied in the form of air by aeration. And BOD oxidation reaction, it produces carbon dioxide, water, and then it also creates new cells. Like we humans, when we eat food which is organics, the cells grow, and that's how the little children, they grow and cells grow. And then also it gives rise to energy that helps the microorganisms to move around, to collect food and to carry out their essential activities, a good part of which is reproduction. And it is the reproduction process which produces new cells. And oxygen is supplied in the form of aeration, and 1 kilogram of oxygen or 1 pound of oxygen is necessary for every pound of BOD. And there is a growth of production of new cells, and this ratio is, the growth ratio is expressed as Y, or growth yield coefficient. 60 to 75% of the BOD that is in the wastewater is utilized in the growth of new cells. So where does the remaining go? That is, the remaining part is oxidized to produce the energy, which is given in the equation as minus delta E. As opposed to BOD oxidation, the nitrification reaction is multi-stage. Here TKN, which consists of ammonia and organic nitrogen, that is first broken down. Majority of it is about 60 to 80% of all the TKN is broken down to ammonia. And then ammonia reacts with water under the suitable pH condition, about pH of water about 6.5 or 7.5 and below, which becomes ammonium ions. Then ammonium ions react with oxygen or oxidized to nitrite. This is a multi-step reaction to nitrite, NO2, hydrogen ions or protons, and water. Then nitrite reacts further with oxygen to produce nitrate. So as you can see, nitrification reaction, there is a net production of hydrogen ions or acidity. That's why the nitrification reactions tend to depress the pH, because hydrogen ions give rise to acidity of water. It depresses the pH, and in order to counteract that, you have to add some alkalinity, which neutralizes the acidity. Now, many wastewaters, or majority of wastewaters that come into the treatment plant, do consist of some buffering capacity that consists of the alkalinity. So then that can be neutralized by this buffering effect of the alkalinity. If not, then you have to supplement the alkalinity. So as you can see, 7.14 grams of alkalinity as calcium carbonate is necessary to counteract the acidity that is created by nitrification of every gram of ammonia, and then 4.56 kilogram of oxygen is needed for every kilogram of ammonia oxidized. And the growth in case of nitrification is very slow, is very low growth rate. It is only 0.12 gram of new cells per gram of ammonium oxidized. And final product is nitrite plus non-biodegradable TKN. As I said, only 60 to 80% of TKN is converted to ammonia, and there is a part of TKN, organic nitrogen, that is not degraded. So that is the non-biodegradable TKN that remains with the wastewater. Okay, this shows the mechanism of nitrification and denitrification. So as nitrate is produced, then to remove the nitrogen, for total nitrogen removal, you have to go to the next step, which is denitrification. And denitrification is done, as you can see from these reaction steps. Denitrification is done by adding some organic substrate, typically methanol, where nitrate is consumed by this organic substrate, and that produces nitrogen gas, and nitrogen gas is emitted, that is removed from the waste, because it is gas, it's removed from the wastewater. So the final discharge is free from any nitrogen, and that is a major means of mitigating the eutrophication issue encountered, or that is created by point discharges of wastewater, treated wastewater. About 4 kilograms of BOD or organics are consumed per kilogram of ammonia nitrogen. Now, the benefit of denitrification is that about 50% of oxygen that is consumed for nitrification is returned, because as you can see that nitrate supplies the oxygen for denitrification. So about 50% of the oxygen that is consumed for nitrification is returned as credit for denitrification, and 50 to 60% of the alkalinity is returned by denitrification reaction. And this triangle diagram shows the nitrification and denitrification steps. So a commonly used nitrification denitrification reaction, the reactor is, as you can see, the influent coming into first the denitrification reactor, also called selector, and then here the nitrate that is formed in the aerobic reactor is returned at internal recycle, and also the return activated sludge from the clarifier is returned here. So it takes care of the denitrification of the nitrate, and then the organic part of the wastewater is removed in the BOD removal part. Then the ammonia is oxidized to nitrate. And as you can see, this nitrate is returned here in the denitrification, or also called pre-anoxic reactor, where denitrification is done. Typically, you can achieve about 4 to 5 milligrams of total nitrogen by this kind of process, which is also called modified Lutzer-Ettinger or MLE process. Then if you want to go beyond the total nitrogen limit of total nitrogen of 5 milligrams per liter, then you have to add post-anoxic stage, where methanol or another organic substrate is added from external source, and this is called post-anoxic reaction, and then any residual methanol is oxidized in the post-aerobic polishing reactor, and the clarifier conducts solid liquid separation. So what I just described is the basic suspended growth process, and then there are fixed swing processes, which I stated before: trickling filter, where these media are stacked in the reactor and as a filter, and water is distributed from the top by some distribution arms which rotate continuously, and air is supplied from the bottom. And this is on the right, you see RBCs, or rotating biological contractors. This is an example of dynamic fixed swing process, where these arms, where these discs which are mounted on horizontal shafts, they rotate and they continuously come in contact with air, and also they are dipped into the water that is in the trough, which is supplied by the wastewater, and that's where the growth of microorganisms take place, and they are attached onto the disc surface. And MBBR, which is the latest development on dynamic fixed fill processes, it consists of media which are themselves suspended in the wastewater treatment reactor. And you can see MBBR reactor consists of media, and on the left you can see the film on the media surfaces. This is the BOD removing microorganisms, and on the right there are nitrifying microorganisms, and these films, they develop on the internal surfaces of these media. These media are made up of HDPE, high density polyethylene, which is plastic, and you can see the examples, the pictures of the media, and there are different shapes and sizes of the media, and these are the core offerings of Headworks International, the company that we represent. From this point on, I request Mr. Siva Angappan to continue with the next part of the presentation.
Thank you, Sam. Matthew,
Thank you.
please. My name is Siva Angappan. I'm the Director of Process Engineering for Headworks. I handle the MBBR and IFAS design and application engineering. So Dr. Sam presented you the basics and the basic science behind the nutrient removal. I'm going to be talking about a couple of case studies and the basics of the MBBR technology specifically. So MBBR technology involves use of floating media. So we have different types of media in our product lineup. So we started with the AC450 on the bottom left. That's the media that was invented by us in year 2000. And since then, we have made multiple versions of the media, with each one with a different type of surface area, different openings, different fluid dynamics in it. So each one you have some advantages, but they're all very similar in the sense that they're all made of HDPE, and they all also freely move around in the tank, which makes it more efficient, because you will have efficient mass transfer of oxygen and BOD, ammonia, all the substrates into the media or biofilm. So what you see on the bottom right is the biofilm on the media. You'll see that the ActiveCell 450 has larger openings, and you will see that the rightmost point is where the BOD biofilm or heterotrophic biofilm exists. It's a brown and brownish color, grayish color. On the bottom, you'll see the ActiveCell 450 with the nitrification biofilm, which is reddish in color. Typically, the larger openings can handle much higher loadings compared to smaller openings, which will have lower loadings, which may have specific applications in ammonia removal or nitrates removal. Whereas industrial applications with high loadings and high temperature, typically the larger opening media is used. They all have a specific gravity of 0.94 to 98. What that means is that it's less than water. So any media, when you put it in the tank, it will float. When you start aeration or mechanical mixing, the media will start to mix. When the biofilm gets onto the media, so the specific gravity will gradually increase towards 1. It will be still 1 or less, but it's almost close to 1. So it's called neutrally buoyant. It's very easy to mix because it's same specific gravity as water. For that reason, we don't use any mixing energy. All we need is the air required for oxidation of the materials. That's more than enough to mix the media in the tank. These are the components we typically supply. These are the core components. These are the components inside the MBBR IFAS reactors. We supply all of this and the engineering behind it and the process guarantee also. So anything outside the reactor, we are flexible on the scope of supply in terms of to supply by us or to be supplied by customer or engineer or contractor. So inside the reactor, we place the media. The media can be anywhere from 10 millimeter to 30 millimeter in shape, in different shapes. The aeration grid in the bottom of the tank provides the air for oxidation, and which is more than enough for mixing. And you see the retention screens in the bottom middle. Those are the screens that keep the media inside the tank. Those typically have 8 millimeter openings. So if we have a 6 millimeter screening in front of the MBBR reactor or in front of the primary clarifier, it will prevent all the solids getting into any solids greater than 6 millimeters to get into the MBBR IFAS reactor. And any solids biomass produced in the MBBR IFAS reactor is small in size and go through the retention screens, but media will stay inside. In case of anoxic reactors or anaerobic reactors, we use mechanical mixing. These are specifically made to work with the media in it, but we can also use the anoxic zone without media to save costs. So these mixers are made of stainless steel. They have a banana blade type mixers at slow RPM, and we have specific modeling programs to design it and position it within the reactor. So why MBBR or fixed film process? The main reason is that it's self-regulating biomass. They are basically the bacteria will grow and shrink depending on the load that comes into the reactor. So there is no need to adjust the return flows or any other parameters within the tank. The biofilm will automatically shrink and grow depending on the load. So it allows for flexible designs. So you can upgrade existing system. You can retrofit existing tanks. If we are doing only BOD removal, for example, we can, within the same tank, we can add on nitrification, denitrification, as well as phosphorus removal. In a pure MBBR process, you don't need any kind of operational adjustment for anything inside the tank. What I would need to do is outside the tank, like pumps and blowers, those kind of things. When you have a high load variation, the biofilm automatically sinks and grows. So it's very stable under large load variations. And the most important thing is the very small footprint. If you have experience with activated sludge plants, we can shrink the footprint by a factor of 4. Or increase the treatment capacity by a factor of 4. So either way, we can combine those two, increase treatment flow capacity or meet new regulations for nitrogen phosphorus removal within the same existing tank. So again, MBBR IFAS processes are highly customizable. You can add one module at a time. If you already have BOD reactor, you don't want to disturb the process, you can add a nitrification process in the back end or a denitrification process in the front end. So we can also add a anaerobic reactor in the front end for phosphorus release and removal in the aerobic zones. So the design parameters for MBBR processes is a biofilm process. It's dissolved oxygen, typically 2 to 3 milligrams per liter. We're doing nitrification for our removal of ammonia, we can have a DO of 3 to 6 milligrams per liter. Generally speaking, 6 milligrams per liter is on the high side, and it's used only at very low temperatures. At high temperatures, we can use a DO of 3 milligrams per liter for nitrification. For BOD, we can use 2 in high temperature situations. And then nutrients are, as Dr. Som explained, every living thing needs nutrients, including bacteria. So they generally have a fraction of BOD to nitrogen to phosphorus ratio of 100 to 5 to 1. If we have more than that, you will have to remove the nutrients to meet the requirements. If you have less than those fractions, then you have to add nutrients. So for industrial waters, we tend to add nutrients for most industrial waters. Some industrial waters like meat, poultry, those they'll already have the nutrients. Retention time is another factor. Typically, Biofilm processes have a retention time of 2 to 4 hours, including nitrification at warm temperatures. In cold temperature, it can be up to 4 to 8 hours. And loading rate is the most important parameter for biofilm design. Typically, for BOD removal, it can be 15 to 25 grams BOD per square meter per day. So it's basically add up all the square meters, the surface area of the media in the reactor, and use that. We tend to use only the internal protected surface area, but a lot of vendors try to use total surface area. So in our experience, we have not seen any kind of biofilm on the external surface area, so we don't count that in our design. For nitrification, the rate can be from 0.5 to 1.5 grams of ammonia and nitrogen per square meter per day. So the difference between MBBR and IFAS is the recycle. If you schematically, only the recycle of the active sludge is the only difference. But in process-wise, there's quite a bit of difference. So when you add the recycled active sludge, your bacteria back into the tank, you're recycling the bacteria. So when you're designing for IFAS with the return active sludge, you usually have to consider how much you recycle and what's the amount concentration of bacteria in the suspended in the reactors. So those are two extra design parameters. These are suitable for retrofitting existing active sludge systems or to shrink the footprint and to reduce the cost. Clarifiers are cheaper compared to DAF, for example, DAF, but clarifiers occupy more space. But in IFAS, the reactors take less space. So in terms of overall footprint, MBBR or IFAS are somewhat close to each other, but if you have an existing active sludge, it's much easier to retrofit by adding media and including aeration requirements. If you're building a brand new plant or a small plant or an industrial plant, the ideal technology is for MBBR without recycle of sludge, because the industrial plants operators don't want to spend too much time running the wastewater plant, so they minimize the operation time by not having to recycle, monitor MLS. It's a very simple to operate, single pass. IFAS is a little bit more training required for the operators, but it can help in when you have an existing plant, you want to increase capacity or meet new requirements within the same time. So the drivers again, IFAS, you would use that to upgrade existing plants, or if you want to incorporate phosphorus removal. For phosphorus removal, we need suspended bacteria to release the bacteria, release the phosphorus in the anaerobic reactor when they're stressed. So for that, you need the IFAS process with the recycled sludge. MBBR, typically for municipal plants, existing plants, it can be add-on process. Either post-nitrification, if you don't want to disturb the existing process, you want to add on nit or denit in the back end after the secondary clarifier, we can add that. Or you can add it in front of the current existing system to add it as a roughing reactor to increase capacity. This is typically used in industrial plants when they have a production doubling within 1 or 2 years. They don't want to build an entirely new plant, so they can put a roughing reactor with 1 or 2 hours of retention time in front of the active sludge system, and then take out 50 to 60% of the BOD upfront, so that the existing system can handle the remaining load. Or if you are upgrading trickling filters or BC plants, then MBBR is ideal technology because operators are already familiar with it. The issue with the trickling filter is that it's uneven distribution of BOD, aeration, all those things. They will have a lot of septic zones or anaerobic zones, which can give rise to smell and other issues like worms and insects. RBC plants, the main issue is that a lot of moving parts in the reactor, so they are prone to failure. Typically, RBC plants the bearings will have to be replaced every 5 to 10 years. Whereas an MBBR plant, inside the reactor, there are no moving parts. So there is no need to maintain anything inside the MBBR reactor for more than 20 years. The media, aeration grid, retention scheme, they are all designed to last more than 20 years, 20 to 30 years. Again, the benefits of this biofilm technologies is if you have site constraints, you don't have any room to expand, you can easily put in an MBBR or IFAS plant within the existing tanks. And the next advantage is that it's resilient to highly variable flows and loads. The biofilm automatically shrinks, grows, and adjusts to the new load conditions. Then it can also handle low flow conditions. If you have an activated sludge plant and running at only 20-30% of the load, and your suspended growth bacteria will die off. Whereas in MBBR IFAS plants, the bacteria survives on the biofilm as many days as like 3 to 7 days. So even after 7 days, the MBBR can come back to life really fast, because the biofilm is strongly attached to the media, and they survive using endogenous respiration and wait for the new load to come back. So when the new load comes, it will automatically grow and meet the new condition really fast within as few hours. And it's easy to upgrade in a modular fashion. If you have a existing plant, you don't know how much the future capacity is needed. You can start with a small fuel fraction in the reactors and then gradually increase it to meet the new loads or flows in the future. So the advantages are, I won't go through all of that, but you will have a couple of things I didn't touch are the MLSS, for example. The MBBR biofilm is equivalent to up to 5,000 milligrams of MLSS. So what that means is that if you have a suspended phase activated sludge system, you already have 2,000 to 3,000 milligrams per liter. We can triple it by adding 5,000, 6,000 milligrams of MLSS onto the media biofilm. And then the one thing I did not talk about the toxic shocks. If you have a toxic chemicals going through the reactor, the biofilm can withstand those toxic chemicals much better because the biofilm is actually hundreds of layers of thickness. So only the top layers die off and the bottom layers survive back. One common problem with activated sludge systems is the sludge bulking or due to filamental bacteria that can cause a lot of issues for the activated sludge systems. Can cause a lot of foam and thick foam and difficult to settle in the clarifier. So all those things can be avoided with the MBBR, efficient operation of the MBBR IFAS plants. So IFAS again is the recycle is the main difference schematically, but you will have to maintain the MLSS and RAS flows to account for the suspended phase bacteria. So when you have an IFAS plants, there are actually two processes running within the reactor. The biofilm process, which acts independently of the suspended bacteria process or activated sludge process. When you incorporate the biofilm in an activated sludge system, we can design it so many different ways. One of the ways is to have both of them, both BOD removal happen in the same matter. If you size it appropriately, we can remove all the BOD in the suspended phase and all the ammonia in the media. So we can combine process in one reactor by incorporating the biofilm in an activated system. MLSS, when you have an IFAS process, we can run it anywhere from 1,000 to 3,000, depending on the requirement. When you convert an activated sludge into an IFAS process, we can actually offload the clarifier. If your activated sludge system is struggling and your clarifier is struggling to meet the solids loading requirement, we can actually reduce the solids loading to the clarifier and take on more solids or MLSS on the media. That way, if you're running at 3,000 MLSS, you can offload the clarifier to lower MLSS to 2,000, and we can take a lot more MLSS on the media, which sloughs off periodically. Typically, the solids coming out of the biofilm is only 10% of the total solids going to the clarifier. Your clarifier solids loading is reduced. So to summarize the conversion part of the existing activated sludge plant, we can, if we have, for example, if we have 50,000 gallons, about 200,000 liters of capacity, 200 cubic meters of tank volume, and you're doing only BOD removal and treating 10,000 cubic meters per day of wastewater to meet BOD and TS limit. We can, to give you an example, we can convert this plant into a nitrification plant, adding ammonia removal and also increase the capacity, flow capacity by 50-60%. We can do all that within the same tanks, meet the new requirements for ammonia removal within the same footprint, and we can increase the capacity also. So we went down from HRT of 4.8 to 3.2 hours, increased the capacity basically 50-60%, but we also met the ammonia removal required. So this is a typical example, but we can also add a total nitrogen removal with the anoxic and also phosphorus removal with the anaerobic zones within the same tanks. So in the warm weather, we can do all of this complete BNR, biological nutrient removal, within 6 hours of retention time. In cold weather, it can be as high as 12 hours. So that's typical activated sludge system designed for only BOD removal, but we can do complete BNR removal within the same tank. So I want to do a couple of case studies. So first case study is Batesville, Arkansas. It's a lagoon-based process, pre-treatment process. So as the population increased, the lagoon was struggling to meet even the BOD limit. So they were the BOD limit was originally was 30 milligrams per liter, but they were not able to meet that limit. The BOD in winter was getting up to 50 milligrams per liter. The main reason was that one reason was that in winter the temperature is very low, can be 4.5 at the lagoon, and as over the years the population grew and the industries around the plant grew, so they had to expand this plant. So they looked at multiple options. Then they chose MBBR primarily because of the small foot. So we designed a two-stage, two-train system. So the system is designed for 40 MLD, and we designed 20 MLD in each train. First stage for BOD polishing to get the BOD down from 50, 60 to down to 10, and the second stage for ammonia removal to meet the ammonia less than 8. Even though ammonia limit is less than 8, as we will see later, we routinely meet ammonia less than 0.5. So the flow is highly variable depending on the season. Here we're showing from December to March during the startup time. When there is heavy rain, the lagoon fills up very fast, so we have to process much more flow. So it can be as high as 40 MLD. Or in dry season can be as low as 4 MGD, or which is 15 MLD. So in terms of operating data from October to March, you'll see that October the temperature is around 20 degrees. As the winter arrives in January, it can be as low as 5 degrees C. So it's a highly variable temperature, and that causes kinetics problems for the lagoon system. So MBBR can handle this temperature variation much better than any other process. And as the temperature drops, BOD also increases into the MBBR after the lagoon, and ammonia starts to increase as well. Next slide, please. This shows the ammonia concentration with the temperature in comparison to temperature. So in summer, most of fall, and most of spring seasons, ammonia is taken care of by the lagoons. But as the winter approaches in November, for example, the ammonia starts to increase. And once the winter is in full swing in January, the ammonia suddenly spikes all the way from 0 to 35 milligrams per liter. So the MBBR has to adjust to the going from no BOD, no ammonia, to suddenly a lot of BOD, a lot of ammonia during winter. So you'll see in the later on the data, MBBR is ideal process to handle this kind of variations. Here you see the ammonia in and out of the MBBR system. You can see that ammonia slowly starts to rise in November. It goes as high as 35 milligrams per liter, whereas the green triangles are the ammonia effluent, which is always close to 0. So next case study is Mora, Minnesota. This is the first MBBR plant in a municipal utility in North America. This was built around 2001 and started up in 2002. So this plant shown at the bottom of the picture is the pure oxygen plant, actual sludge plant, and they were using the lagoons or ponds for polishing the wastewater after the pure ox plant for BOD polish. Similar to the Batesville plant, the population increased. Also, industries grew, so they were not meeting the BOD limit. So they wanted to build a new MBBR plant. So we did a extensive pilot testing on this plant for ammonia removal and built a new small ammonia removal MBBR plant shown in the middle of the slide piece. So this shows the close-up view of the MBBR plant. This is 10th or 1/20th the size of the actual sludge plant. Here we are looking at close-up view of the data winter only. You'll see that the flow around March 1st in the bottom of the picture. See that the black line flow increases suddenly. This is because of all the snow and the road melting coming to the wastewater plant. And ammonia shown on the gray line, also in winter, it's very high as 50 milligrams per liter. And the temperature shown in the red is very low, typically as low as 5 degrees C. And when we have a sudden increase in flow, drop in temperature, and increase in ammonia concentration, the effluent ammonia is fairly constant, the yellow line at the bottom. So it's a very stable process, can handle variations in high variations in temperature, as well as the flows and loads without displacing the biflow. Yeah, this shows the variations in flow. Blue dots are the variations from, you can see the x-axis is the January 1st to December 31st. And the first spike comes when the snow melts happen around March. The second spike comes in summer rain season. The third spike in the fall. So with the tripling of the flow, even with the tripling of the flow, we cannot wash out the biflow. Active sludge can be washed out. This shows the operating data in terms of ammonia. Blue is influent ammonia concentration, red is the effluent ammonia concentration. You'll see that it's a fairly consistent performance throughout the year, regardless of what's coming in, regardless of the dropping temperatures. To summarize, nitrogen, phosphorus are nutrients required. Too much nitrogen, phosphorus in the water streams or rivers can cause a lot of issues for the living things in those streams and rivers. Primary reason is that it can grow algae, which can cover the entire surface and then deprive the living things of oxygen. Or it could be ammonia taking out all the oxygen in the water. So the living things like your fish and other organisms cannot survive in that environment. Now I'll let Dr. Sam to summarize more, and then we'll conclude the presentation.
Thank you, Siva. We are already past the time. I just wanted to mention here that the subject of biological nutrient removal is pretty vast, and it's very difficult to cover all aspects of it within this short time of 1 hour. And we have limited this presentation to only nitrification and denitrification, and primarily focused on nitrogen removal. But as we said right at the beginning, that another major nutrient is phosphorus, and phosphorus removal is also being called for by the regulators along with nitrogen removal. We did not cover it, so there are many treatment plants that remove phosphorus alone or both nitrogen and phosphorus, depending upon what the regulations call for. And we look forward to another presentation that will deal with phosphorus, biological phosphorus removal and chemical phosphorus, and also integrated nitrogen and phosphorus. So please stay tuned. Thank you for your participation, and please feel free to send us any questions. Our point person is Mr. Matthew Banzer. Through him, please send us the questions, and we'll be happy to answer. Thank you again. Bye-bye.
Of course, everybody have a great day.